what do we actually do with an NMR then? There are three pieces of information that we get from every signal in an NMR. Three pieces of information that we get from every signal in an NMR. And we must analyze all three pieces of information. You may not skip over any of these to try and take a shortcut and save time. It won't work. It'll end up just taking you longer to solve the structure. So you have to analyze all three of these pieces of information. And what we're going to do is we're going to use the three pieces of information from each signal. So again, in this NMR, we have 4 signals. So we're going to analyze all three pieces of information for all 4 of these signals. And we're going to use that information to build puzzle pieces for each signal. And those puzzle pieces are going to tell us something about what functional group the signal represents, and also what is next door to that functional group. I'll talk about that in a little bit. But what we're going to do is we're going to take the pieces of information from each signal, and we're going to build puzzle pieces. So I'm just going to do a silly example. So it tells us something about the functional group that we're looking at, and something about how it's connected, what's next door to it. And so we'll do that for another signal, and so it might tell us something about the functional group and something about what's next door to it. And we're going to build these puzzle pieces this way. Each signal, all three pieces of information from each signal is going to tell us something about the functional group of the molecule and what's next door to it. And then what we're going to be able to do is look at these puzzle pieces that we've built for each of the signals, and we're going to start putting them together. So this puzzle piece could come over here. It looks like this one fits here because we know something about the puzzle piece and what it's next door to. And then this one looks like it fits here. And so we're going to take these puzzle pieces and put them together to build the ultimate structure of the molecule. That's a silly example, but we'll see how that works when we start to actually solve some of these spectra. Okay, so what are these three pieces of information? The first piece of information that we get is called the chemical shift. The chemical shift is the x-axis value for each signal. So if we're looking at this NMR, this one looks like it's about 4.1 or so. This one looks like it's right around 2. This one's, I don't know, 1.9. And this one looks like it's at, 0.9. What's interesting is the exact x-axis value doesn't really matter. What matters is what range it's in. So in a separate video, I'm going to tell you about the 9 or 10 NMR ranges that you need to know. And so all we need to know is 4.1 ppm falls in the 3 to 4.5 range. And that'll tell us something. We'll talk more about that a little bit later. The 0.9 signal falls within the 0 to 2 range. So that's what we need to know. The x-axis for each signal, what range does it fall in? What does that mean? The x-axis, remember, tells us how much energy was required to flip the spin of the nucleus. And what that really tells us is what kind of functional group we're looking at. Each functional group is going to change something about the amount of electron density around the proton, so it's going to change the shielding, which is why each signal has a different x-axis value. And by knowing what range it falls in, certain functional groups characteristically have NMR signals in certain ranges. Again, I'm going to talk about that in a later video. The next piece of information that we get from every signal in the NMR is the integration. And the integration is the area under the curve. So it can be hard to see, but if I zoom in on one of these peaks, notice that these signals are not discrete lines. It's one continuous signal from left to right. So the signal is coming along this way, and then it goes up, and then up again, and then up again. And so we get a continuous curve, which means there's a non-zero area under the curve for each of these signals. And the integration measures the area under the curve for each signal. And what that tells us is it tells us the number of equivalent hydrogens represented by that signal, or by that signal. It tells us the number of equivalent hydrogens represented by that signal. How many equivalent hydrogens caused that signal to appear? So let's take a look at that for a second. if we look at a molecule, I'm just going to make up this molecule. Let's call this one, let's say this molecule, 3-methyl pentane. If we look 1, 2, 3, 4, 5, this molecule has 6 carbons, so its molecular form would be C6, H14. Okay, so if we look at this molecule, we can ask a couple of questions. We can ask how many hydrogen NMR signals would we expect for this molecule, and we could talk about what their integration might be. So integration tells us the number of equivalent hydrogens represented by a signal. So what does it mean to be an equivalent hydrogen? If we look at the 3 hydrogens on this methyl group, I'm not going to draw the H's in, but those 3 sticks represent the 3 hydrogens. Would we be okay saying that those 3 hydrogens are equivalent? As the carbon-carbon bond rotates, those 3 hydrogens become indistinguishable. There's nothing that distinguishes any one of those hydrogens from the other. So those 3 hydrogens are equivalent to each other. So they have identical properties, including identical shielding, identical amounts of electron density around the nucleus. And if they have identical shielding, then that stands to reason that those 3 hydrogens should require exactly the same amount of energy to flip their spin. And if those 3 hydrogens require exactly the same amount of energy to flip the spin, then it stands to reason that those 3 hydrogens would all show up at exactly the same x-axis value and all be represented by exactly the same signal. So those 3 hydrogens cause one of the signals to appear. That signal would represent those 3 hydrogens. So the integration for this signal would be 3 hydrogens. There would be 3 hydrogens represented by that signal because those 3 hydrogens are equivalent. If we look at, say, this hydrogen on this carbon, that's the only hydrogen on that carbon. There's no other hydrogens on that carbon, so it stands alone. There are no other hydrogens equivalent to that carbon. So that one hydrogen still requires some amount of energy to flip the spin. It's going to be a little bit different than the methyl group because it's in a little bit different environment, so it's got a little bit different shielding, so it'll have a little bit different x-axis value, a little bit different chemical shift, and that one hydrogen would cause a different signal to appear, and that signal would represent that one hydrogen. So the integration for that signal would be 1H. Now, if we look at this methyl group over here, these 3 hydrogens, those 3 hydrogens are equivalent to each other for the same reason the original 3 hydrogens were. But what's interesting about this molecule, did you notice this molecule has a plane of symmetry? This molecule is symmetric. And if this molecule is symmetric, then not only are those 3 hydrogens equivalent to each other, but they would also be equivalent to these 3 hydrogens on the other side of the molecule. If I flip this molecule over like a pancake, there's no difference between the methyl group on the left and the methyl group on the right. They are identical methyl groups because of the symmetry in the molecule. So because there's global symmetry in the molecule, all 6 of those hydrogens on those 2 methyl groups are equivalent to each other. They are interchangeable, completely interchangeable because the molecule is symmetric. The 3 hydrogens on each carbon are interchangeable because of the rotation around the carbon-carbon bond, making those 3 hydrogens equivalent to each other. And the 2 methyl groups are further equivalent to each other because of the symmetry in the molecule. So all 6 of those hydrogens are equivalent. If they're all equivalent, that means they all require exactly the same amount of energy to flip the spin, which means they're all represented by the same signal, and that signal would have an integration of 6H. That leaves these hydrogens here and here. For the same reason, those hydrogens are also symmetric. They are also equivalent. So all 4 of those hydrogens would require the same amount of energy to flip the spin. They would all be represented by the same signal, and that signal would have an integration of 4H. So for 3-methylpentane, we would expect 4 unique signals. One of them having an integration of 3H, one of them having an integration of 1H, one signal having an integration of 6H, and one signal having an integration of 4H. We'd expect 4 unique signals. If we look at the NMR spectrum shown here on this slide, it's not the spectrum of 3-methylpentane, but we do have 4 signals. And so the integration, when you get a spectrum, can be represented in one of 2 ways. It can either be represented by numbers written near the signal. So this tells us the integration that corresponds to each of those signals. It tells us how many hydrogens are represented by each of those signals. Or it might be represented by this continuous red line that runs along the spectrum. And so what this is doing, integration, remember, is area under the curve, so it's counting the number of pixels under the curve on the computer screen. And so what it's doing is as the computer goes from left to right, as it gets to a signal, it starts counting up the number of pixels under the curve. So we started back at the left side, and starting from the left, there were no pixels under the curve, no pixels under the curve, no pixels, so relatively flat, staying around 0. Here, now there's a actual signal, so the integral curve jumps up because it's counting the number of pixels under that curve. Then it goes along for another region where there's no signal, and then another signal, so that jumps up again, and jumps up again, jumps up again. So each vertical jump is represented by one of the signals, and that tells us how many hydrogens are represented by that signal. The vertical portion of the integral curve is proportional to the number of hydrogens represented by the signal. So how do we analyze something like this? We can kind of do some eyeballing and some comparison. So when I look at this spectrum, I see that this line and this line are like the same length. They're the same height. So however many signals are represented by this signal would also be represented by the same number of hydrogens. The area under the curve is the same for both signals, so the integration of both of those signals should be the same. Similarly, the height of this line and the height of this line are also about the same height, so the integration of both of those signals should also be the same. The number of hydrogens represented by each of those signals, whatever it is, should be the same. So how do I know how many hydrogens are represented by that signal? So what we can do is we can kind of eyeball it. As I look at this signal on the right, it kind of starts here at this horizontal grid line, and that's why these horizontal grid lines are on here actually. And it looks like it goes up to about 2.5 blocks. So we can say that this vertical line represents about 2.5 blocks vertically. And if I look at this one, it kind of starts here at this block and goes down to about here. It's a little bit more than 1.5 blocks. If I look at this one, it's a little bit more than 1.5. It's more kind of like 1 2/3 blocks. So the integration of these signals, the blue integration appears to be 2.5, and the green integration appears to be 1.6. So that means that this one should also be 2.5, and this one should also be 1.6. Now, the integration tells us the number of hydrogens represented by that signal, the number of equivalent hydrogens represented by that signal. So that would imply that the blue signals represent 2.5 hydrogens. But you can't have half of a hydrogen. So the integral value has to be a whole number of hydrogens. It has to be. You can't have half of a hydrogen. But this tells us that it's 2.5 hydrogens. So what does that mean? Well, the integral curve is proportional to the number of hydrogens. It doesn't exactly tell us how many there are. It's proportional to the number of hydrogens. So what we do is we take these eyeballed numbers and we start scaling those numbers in order to get whole number ratios. So the first thing that we always do is we always divide by the smallest. And if I divide by the smallest, 1.6 divided by 1.6 gives us 1, and 1.6 divided by 1.6 gives us 1. And if you happen to divide 2.5 by 1.6, you end up with 1.5. So 2.5 divided by 1 2/3 happens to end up being 1.5. So that tells us that the green signals represent 1 hydrogen, and the blue signals represent 1.5 hydrogens. But again, you can't have half of a hydrogen. So after we divide by the smallest, we then scale the integrals accordingly. So if I then multiply all of these by 2, this becomes 2 hydrogens, the green ones become 2 hydrogens, and the blue ones become 3 hydrogens. Now I have a whole number ratio. So this is the integration for this NMR. If I add those up, 2 plus 3 plus 2 plus 3 equals 10 hydrogens. The number of the sum total of the integration values should add up to the number of hydrogens in the molecule. It's hydrogen NMR, so it should be looking at all of the hydrogens. So if there's 10 hydrogens in the molecule, then there should be 10 hydrogens in the integration. That works when the integral curves are relatively easy to read, but sometimes you may get signals that are a little bit harder to eyeball. Maybe one is significantly bigger than another, like 9 times bigger than another or something, and that's harder to eyeball. So what we can always do, and this will always work, is we can always get out a ruler and measure the heights of these curves in millimeters, and then do the same thing, divide by the smallest and scale accordingly, and we should get back to this 2 to 3 to 2 to 3 ratio. And if you remember, these NMRs are the same. They're of the same structure. And if we look back here, in this version, I had given you directly the integration value 2H3H2H3H. So the integration value was given to you in this NMR Here it was given by the integral curves, but we should get to the same answer because they are the same spectrum. Okay, so that's integration. The last thing that every signal gives us is the multiplicity, sometimes called the splitting. This is the number of peaks within each signal. The number of peaks within each signal. So if I look at this NMR, the peak over at the left, just above 4 parts per million, has 3 peaks within the signal. And if there's 3 peaks within the signal, we call that a triplet. The peak right around 2 has 1 peak within its signal, and so we call that a singlet. The peak here just below 2 has 1, 2, 3, 4, 5, 6 peaks within its signal. We call that a sextet. And the peak on the right, again, has 3 peaks within its signal, and so that's a triplet. So the number of peaks within the signal is the multiplicity or the splitting. And so you'll have at least one, a singlet, but you could have 2 peaks within the signal, a doublet or a triplet. 4 peaks within the signal would be a quartet, and then a pentet, a sextet, a septet, octet. Doesn't really matter how many peaks you have within the signal. That's what the multiplicity is. It tells us the number of peaks within the signal. And what this tells us is it tells us the number of hydrogens on the neighboring carbon. And that is really cool. That's really important information. This is the first time in any of our spectroscopy that we've gotten information about what's next door. We've gotten lots of information about the functional groups, how many hydrogens, what functional group it is, but never where it is in the molecule, never what it's next to, never what it's connected to, never what its connectivity is. This multiplicity, the splitting, is the first time that we get that, so it's very, very important. So I'm just going to go ahead and give you the answer here. If we have time in a later class, I can talk about why this is true, because it's actually a really interesting story, but I'll just tell you the answer. So you look at the number of peaks within the signal, minus 1 equals the number of neighboring hydrogens, the number of hydrogens on the neighboring carbon. So if I look at this triplet, the triplet has 3 peaks within the signal, 3 minus 1, so that tells me this has 2 neighboring hydrogens. The carbon next to whatever this is has 2 hydrogens on it. The singlet has 1 peak within its signal, so 1 minus 1. The singlet has 0 neighboring hydrogens. That means whatever this is, whatever's next door to it, doesn't have any hydrogens of its own. That's not as unusual as you would think. We'll see lots of examples of that as we go through. The sextet has 6 peaks within its signal, and so that means 6 minus 1, it has 5 neighbors. Now that's really interesting because you can't have 5 hydrogens around a carbon. So I want you to think about how you can get 5 hydrogens on a neighboring carbon if you can't have more than 4 hydrogens on a carbon. Think about that. And then this is a triplet, so 3 minus 1 also has 2 neighbors. So that's what we get. For every signal in the NMR, we're going to look at the chemical shift, the integration, and the multiplicity. So we're going to next solve this NMR. I'm not going to do that in this video, we'll do that later, but we're going to figure out how to do that. How do we take this NMR, figure out what the chemical shift, the integration, the multiplicity tell us? How do we draw a puzzle piece for each of the 4 signals? And then how do we put those 4 puzzle pieces together to figure out what the structure of this molecule is? We'll do that at a later time. But this is an overview of how we look at and how we read an NMR spectrum.